Now in the previous lecture we have learned how can we insert a node to a binary heap. So hopefully everything is clear there. Now in this lecture we will learn how can we extract an element from the binary heap. Now let's say we have a binary heap like this and it's basically a minimum heap. Now if you want to extract an element from this binary heap over here, you always need to remember that the only element that can be extracted from this binary heap over here is root node. Now in this case you can see that our root node is 5 in this case. So this means that we are only allowed to extract only this element from here. So if you want to extract, for example, 10 from here, it's not allowed. So in case of binary heap, we cannot extract any child from here. We can only extract the root node from over here. Now here, once this root node is extracted from this binary heap, so in this case you can see that the place of root becomes empty. So this means that we have to promote any other node to the place of root node over here. So let's see how this is working. So let's say we have a binary tree like this and we want to extract a node from here. So as I mentioned, we can only extract a root node. So in our case, the root node is 5. Now if we extract this node from here, the problem is we will not have a root node over here. So we need to do some adjustments to set root node over here. Now in this case, the first step is we will find the last element in our binary heap over here. Now in our case, the last element in our binary heap is 80. Then, after finding the last element, we are going to replace the last element with the root node. So if you replace it with the root node, we are automatically deleting the last element from the binary heap over here. So in this case, we are moving the last element to the place of the root, and we are deleting the last element from binary heap over here. Now after replacing it, we see that binary heap property is violated, which says that in case of minimum binary heap, the root must be less than its children. Now in this case we can easily see that the root in this case is greater than its children. So this means that the minimum heap property is violated over here. So to solve this problem, we are going to create a new method which is called heapify from top to bottom. Now in this case, if we call heapify method for this binary heap over here, we need to replace one of its children to the place of this binary heap over here. Now we can easily see that both of these children over here is less than this root over here. So this means that we are going to select any of these children over here. Now the problem is which one we are going to select. So in this case, in case of minimum heap, we are going to select which one is smaller. So in this case, we see that the left child is smaller. So here we are going to replace it with left child. Now if we replace it with the left child, we see that here again, the minimum heap property is violated for left subtree over here. So here you can see that 80 is greater than 30 and 40, which are the children of the 80. So in this case, one more time, we are going to call heapify method to maintain the property of minimum heap. So here again, we are going to select the smaller child. So in this case, smaller child is left child, which is 30. So we are going to replace it with 30 over here. Now after replacing it, we can easily see that the minimum binary heap property is maintained. So this means that after heapify method, we have maintained the property of minimum heap in this case over here. Now in case of maximum heap, we are going to select the child which is bigger. So with this, we are going to call here again top to bottom heapify method, and we are going to replace it. So here first we need to identify which binary heap is this. Then based on that, we are going to implement operations over here. Now based on this logic, let's head over to Java and create our extract node method for this binary heap over here. Now inside this binary heap class over here, we are going to create a method for extracting a node from binary heap. Now before creating a method, as we said before, for extract, we are going to create another method which is called heapify top to bottom method. So in this case, first I'm going to create heapify top to method bottom, then we are going to use this method inside extract method. So let me just comment over here, heapify top to bottom. So before we created bottom to top, so in this case it's going to be top to bottom. Now here I'm going to declare our method like this. So it's going to be public void heapify top to bottom. Then this method will take two parameters. Now the first parameter will be the current index. So we are going to take the index of the node. So this will be the type of integer, and the second parameter will be the type of string, so in which we are going to select heap type. First we need to identify which heap type is this. Is it maximum or minimum? So based on this one, we are going to implement operations over here. Now here, in case of top to bottom, the index that we are passing over here, the first index will be the root's index, because we are extracting the node from the root and we are moving the last node to the root. So that's why we have to start from the root. So this means that based on this root index, we are going to calculate left and right child's indexes. Then we are going to perform operations on these children over here. So the first variable that I'm going to create will be the left child's index. So we know that in case of binary heap, we are calculating left child's index by multiplying the index by 2. And we are calculating the right child's index multiplied by 2 plus 1. So the next variable will be for the right. So in this case, it's going to be like this. Index multiplied with 2 plus 1. Now after doing so, the next thing that we are going to do, we are going to check that if there is not any child for this node, then in this case we are not going to do anything, we are just going to return. So the first if condition will be like this. So in this case I'm going to do it like this. If size of 3 is less than left, in this case it means that we don't have any child in these 3 over here. So we are just going to return. Now otherwise we are going to continue to check that which type of binary heap is this. So first I'm going to write the conditions for the maximum heap, then I'm going to write for the minimum heap. So the first if condition will be like this. If heap type is equal to maximum, in this case I'm going to start to write the conditions over here. Now here we might have two conditions. The first condition is we have only one child, and the second condition is we have two children. So if the size of the tree is equal to the left index, it means that, so in this case we have only left child for this node, so we are going to do the comparison, and based on this comparison we are going to do swap operation over here. So the condition will be like this. If size of tree is equal to left index, in this case it means that it has only one child, so in this case we are going to do comparison over here. So if this is the maximum heap, if the root node is less than the left child, in this case we are going to swap them, otherwise we are going to return. So in this case it's going to be like this. If ARR with the index, which is the root index, is less than ARR with the index of left, in this case we are going to swap their places. So to swap them, it's going to be like this. Integer temp is equal to ARR index, which is the root value, and ARR index will be equal to ARR left, and in ARR left we are going to set the value of temp. So with this we have successfully swapped these values over here. Now after doing so, we are going to put over here return, because in this case we are swapping them and we need to return them. Now in the else condition, we are going to write the condition in which we have two children. Now in case of maximum heap, if we have two children, we are going to take the one which is greater. So in this case, first we are going to compare the children, and we are going to take the greater child. Then we are going to swap that greater child with the root node if the root node is less than this greater child. So it's going to be like this. If ARR left is greater than ARR right, in this case swap child is equal to left. So here, after this right index over here, I'm just going to create swap child. It's going to be the type of integer, because in this case it will have the index of the greater child or smaller child. So in case of maximum heap, we are assigning it the greater child. In case of minimum heap, we are going to assign it the smaller child. So in this case, in the else condition, we are going to write swap child is equal to right. If the left child is greater than the right child, we are assigning left child to the swap child. Otherwise, we are assigning right child to the swap child. So after doing so, we are going to compare the root node's value with this greater child. So in this case, it's going to be like this. If ARR with root index is less than ARR swap child, in this case, it means that we are going to replace the value of swap child with the root value. So in this case, here again, I'm just going to copy the code from here and put it over here. In the temp, we have the value of root. Then here, I'm just going to put swap child, because we are swapping it with this child over here, and we are setting it like this. Now, after doing so, we have successfully replaced the value of the greater child with the root node. So in case of maximum heap, we have moved the greater childs to the place of root. Now, after doing so, we are going to continue to the condition for implementing minimum heap. So here, I'm going to write else if heap type is equal to minimum. In this case, we are going to implement the same operations for the minimum heap, but in this case, we are going to change some comparisons over here. So what I'm going to do, I'm just going to copy this code from here, from this inside of the maximum heap, and pass it over inside of the if of the minimum heap. Now then I'm going to change the condition. So in this case, here again we have two cases: if we have only one child or if we have two children for the binary heap over here. Now if the size of 3 is equal to left, in this case we are going to do our comparison. So if the root node is greater than the left child, we are going to swap them. So in case of minimum heap, in the root we should have the smaller values than its children, so that's why we are changing it to the greater sign. Then we are going to continue to swap them. Then in the else condition we are going to continue to check that which child is smaller. Now in this case, if the left child is less than right, we are going to assign the swap child left. Otherwise we are going to assign the right child, because we are looking for the smaller child. After finding the smaller child, we are going to check that if the root node is greater than this smaller child, we are going to swap their places over here. Now after doing so, at the end, then we are going to run heapify top to bottom method recursively for swap child. So in this case, it's going to be swap child and heap type. Now with this, we have successfully implemented logic for heapify top to bottom method. Now let's see what's the time and space complexity for this method that we created over here. Now here again, we are going to continue from the beginning of the method. Now in this case, when we are starting this method over here, we are calculating the index of left child, then we are calculating the right child's index, then we are creating a variable over here as a swap child. Now these 3 lines of code will take a one-time complexity. Then we are checking that if we don't have any child for these 3 over here, we are returning, so this part of code also will take a one-time complexity. Then we are continuing to the next part of code. So in the next part, we have if condition to check that if the heap type is maximum. In this case, we have 2 cases: if this node has only one child or it has 2 child. So if it has 1 child, we are going to check that if the root node is less than this child, we are swapping them. Otherwise, we are not doing anything. So here you can see that we are just performing comparisons, and we are just doing some assignment over here. So these lines of code over here will take a one-time complexity. Now here again, in the else condition, we are comparing the left and right child, then we are assigning it to the swap child. So this part of code also will take a one-time complexity. Then in this if condition over here, we are swapping the current node with the swap child. So here also we are just doing the simple assignment statement. So this part of code also will take a one-time complexity. Then in the else if part of the main if condition over here, we are checking that if this heap type is minimum. Here again, we are performing some comparisons and we are doing some assignment over here. So this part of code also will take a one-time complexity, and similarly the else part of this if condition will take a one-time complexity. So as you can see, till here, so till end of this method, all transaction takes a one-time complexity. Now at the end, we are calling this method recursively for swap child. So this means that we are either going to continue to the left child or right child based on the heap type and based on the comparisons that we are doing over here. So this part of code will take a log n time complexity. So this means that the time complexity for this method, if you combine everything together, will take O log n time complexity. Now similarly, the space complexity for heapify method is O log n, because here when we are calling recursively the method, we are inserting these elements to the stack memory. So that's why the space complexity is O log n. Now with this, we have completed this heapify method over here. Now based on this heapify method, I'm going to create extract head of heap. So as I mentioned, when we are extracting a node from the heap, we are only extracting the head of heap. So that's why I'm going to name the method extract head of heap. So this method will return the type of integer, because in this case our heap is integer type. So it's going to be integer, and the name of method will be extract head of binary heap. Now the only parameter that this method will take, heap type. So we need to first identify the heap type, then we are going to call extract method for this heap type over here. Now here, first thing we are going to check that if heap is empty, we are going to call isEmpty method. In this case, I'm just going to return -1, because in this case the heap is empty. Otherwise, we are going to perform the operations over here. Now in the else condition, we are going to create a variable over here and assign the root of this binary heap over here. So we know that the root of binary heap is located at the index of 1. So that's why it's going to be like this. Int extracted value is equal to ARR with the index of 1. So we are taking the root value. Now after creating this variable over here and assigning the root value over here, we need to change the value of the root with the last element in our tree over here. So in this case, the value of root is located at the index of 1, and we are going to set the last element from this heap to this root value. So in this case, the last element is located at the index of size of 3. Now after doing so, we are going to decrease the size of 3 by 1, because in this case we are extracting one element from this tree. Then after doing so, we are going to call heapify top to bottom method with the index of 1, because we are starting from the root node then, and this one will take heap type that comes from this parameter over here. Now at the end, we are going to return this extracted value, because in this case we are removing this value from the heap and we are returning it. But as you remember, when we created pick method, in the case of pick method we are just returning the value from the root node, but we are not removing it. But in this case we are removing it. Now with this, we have successfully created a method for extracting a node from the heap over here. Now let's see how this is working in practice. So as you remember, we have created a binary heap over here and we have inserted 4 elements to this heap over here. Now then we are running level order traversal. So in this case, this is minimum heap. So this means that the root of this minimum heap is 1. So if I run the extract head of heap in this case, it's going to extract the 1 from this binary heap over here. So the type of heap is minimum heap. So after extracting, I'm going to call level order traversal one more time to see the differences. So if I run our code, now after running our code over here, you see that we have an error over here. So inside this method over here, when we are creating swap child, we just need to initialize it as 0. Then we are going to assign values to it. So if I run our code one more time, so you see that first we created our binary heap over here, then we have inserted 5 elements. So in this case, the root node is 1. Then we are calling level order traversal. So from here you see that the root node is 1, then the left child is 5, and the right child is 15, and 10 is the left child of 5 over here. Now after calling extract heap method over here, in this case 1 is removed from here, and you can see that the minimum heap property is maintained. Now if I create a maximum heap over here and call our method, so I'm just going to change this minimum heap to maximum heap to see that in this case how this is working. So in this case you see that the maximum element is 15, so this means that's going to be the root of the heap over here. Then after removing it, 15 should be removed from this heap over here. So if I run our code one more time, you see that in this case 15 is the root node. Now after running it, 15 is removed, so the maximum heap property is maintained over here as well. Now with this, we have successfully implemented extract head of heap method in this case. Now let's see what's the time and space complexity for this method over here. Now before we have learned that for heapify method, the time and space complexity is O log n time complexity. Now here again, we are going to start from the first line of code of this extract head of binary heap. So in this case, first we are checking that if this heap is empty or not. So if it is empty, we are returning -1. So we know that isEmpty method takes O1 time complexity. So this part of code will take O1 time complexity. Now in the else condition, we are creating extracted value and assigning the root value to this value over here. So this line of code will take O1 time complexity. Then in the next line of code, we are taking the last element in the binary heap and assigning it to the root value. So in this case, this line of code will take O1 time complexity. Then we are decreasing the size of 3 by 1. So this one also will take O1 time complexity. Then we are calling heapify method with the index of 1. So we know that heapify top to bottom method will take O log n time complexity. So this line of code will take O log n time complexity. Now at the end, we are returning extracted value. So this one also will take O1 time complexity. Now if we combine all these complexities over here, we get O log n time complexity. Now the similar list space complexity is O log n, because when we are calling heapify top to bottom method, it calls itself recursively, so that's why the space complexity is O log n space complexity. Now with this, we have come to the end of this lecture. So in this lecture, we have explained the logic behind the extract head of binary heap, and we have explained heapify top to bottom method, and we have implemented them in practice. Then at the end, we have learned time and space complexities for these methods over here. So hopefully everything is clear about this lecture. So see you in the next lecture.